connection patterns. Okay? All right. Any other question? All right, I'm going to move on. Can I have the PowerPoint back? All right. So let's go. For series connection, combining loudspeakers, 8 ohms, 8 ohms, 16 amps, it's not great for a 4 ohm amplifier, so that will not work. So move on. Okay, this is what I was trying to tell you before. So you have, as a rule of thumb as well, select a power amplifier output value of about 0.8 to 1.5 the speaker program value. This will work. So you have the power rating, you have noise, you have program, you have peak, and we always say use the program value. And for the example we have here, you have okay, when you connect to an 8 ohm amplifier, you have a 350 watt, 350 watt, 8 ohm, and using the rating of the amplifier there, that will work. Okay, let's go on. So if the benefits of connecting speakers in parallel, number one, you want to increase output compared to just using one speaker per stereo side, and it also gives you the ability to angle a speaker to cover a wider area with sound. So if I had an amplifier, 2 loudspeakers here, for example, and I connect to an amplifier, I can, angle them, better coverage. So that kind of works that way. Okay. So bridge connection is a method of configuring a 2-channel amplifier so that the 2 channels can be ganged or bridged to be used together as on one load. So the purpose of this is to take a 2-channel amp, create a larger single amp that can deliver more power. I think we talked about that already. So let's go on. We have addressed. Okay, so let's move on. Now, a lot of the problems with PA systems are caused by speakers being in the wrong place. Now, some of the issues we could have is things like muddy sound, which means the sound lacks definition, and people not being able to hear, and also feedback, which is a phenomenon we want to avoid at all costs. Now, I will break this down a little bit as we go further. Now, the speakers we have here right now, yeah? We have this, and we have that. So we have a left and right speaker configuration. The reason, this is a standard auditorium, correct? Now, there's sometimes you get into a place where you do not have the access to position your speakers the way you want, correct? So you have to work with what you got, okay? So let's go on. So how do you decide where to place your speakers? So, obviously, I do not, these are my microphones. Let's say these are fixed. Obviously, I don't want to place my speaker. I could have brought that speaker there, maybe put it somewhere around here. You understand? And obviously, the closer it is to the microphones, what are we looking for? Feedback. So you want to keep your loudspeakers as far away from your microphones as much as possible. Now, that's what they call the concept of potential acoustic gain. How many of you are familiar with that? Good, good. So, proximity of the speaker to the microphone, proximity of the speaker to the microphone, proximity of the speaker to the closest audience and the farthest audience, all of that information, and then the number of open microphones combined to affect potential acoustic gain. So if you want to avoid feedback, general principle is that you should keep your microphones as far away from that as possible, or you move, it's either you move the loudspeakers or you move the microphones, but you don't want them to be close together in any way. Okay. Now, you don't want to put your speakers against corners, you know, and that stems from the whole idea of corner loading, basically. So you have very boomy and bassy sound, and your system will not have very good definition. And also, you don't want to keep your loudspeakers very close to the wall. These are actual, situations. So it actually happens. You don't want to keep your loudspeakers very close to the wall. It will be echoey, it will be boomy. You need to give your loudspeakers some room to breathe. Yeah. So you have wall and corner loading. So you have low frequencies radiating from the sides of your loudspeakers, as well as from the front, interacting with the walls to produce an extra boost. So basically, this is the first picture. There is a loudspeaker in a free field. Then you have a wall, a corner, and then a three-wall corner, the floor and the side walls. Now, sometimes people do these things, put their speakers on the corner for a reason. You understand? Let's say I want extra subwoofer boost. It would be a good idea to put my subwoofer at the corner, correct? Yeah. So sometimes you want to use the advantage of corners to actually give your system an extra push, especially for subwoofers. But for the full range loudspeakers, I wouldn't recommend that. Okay. So in a typical auditorium like what we have here, so you can set up left and right, and then you can elevate your speakers in such a way that you can have coverage over the closest seat and the rear seat. Right now we can't elevate, so we have to use what we have. But in churches that, let's say, an installation, I want to raise and rig my loudspeakers, and then I have a certain coverage between the front and the back. So the two axes to consider, obviously, are your horizontal and your vertical. So horizontal is the width, vertical is the depth. So for your horizontal coverage, you're looking at your left to right. We have these loudspeakers covering a certain angle. I think for these loudspeakers, it's 90 degrees horizontal, 60 degrees vertical. Same thing for this one. Now, if you notice as well, because of the width of this space, it will be impossible for this loudspeaker to actually cover horizontally effectively, which is why we have these front fills here to actually compensate for the gap. So usually for standard stereo speaker setup, if we drew this closer and the other one closer, the reason why we put them apart is because of these microphones. We don't want to compromise or to create feedback. So to adjust for that, we have the front fills. But say they were closer. The middle here, because of the summation of the two speakers, you have a 3 dB boost in the middle. So, yeah, this is a question a lot of people grapple with, So stereo or mono, what should my system be? Obviously, we all want that stereophonic sound that we have in our headphones, or maybe at home, you have your surround system or you have your stereo system, and you feel this some instruments coming from the left and right, the dramatic, But then in a church environment or an installation environment, it may not necessarily be the best solution. So for vertical coverage, we're talking about elevation, and if you're using a ground stack with a pole mount, you want to make sure your vertical coverage matches the listening plane. Now, move to the next slide so I can actually explain this a bit further. Now, this is what to achieve a minimum variance of 6 dB. Now, what do we mean by minimum variance of 6 dB? Anybody? Yes. The quietest, yes, between the front and the back, basically. So you have this ratio. So you have 2x, the shorter distance, should be equal to or greater than than y, which is the from the loudspeaker to the rear. So you need to keep that equation, and that way you can always have minimum variance of 6 dB across your listening space. So it's important to know that coverage doesn't have to extend to the entire venue, but only to the part of the venue you want to cover. So what do we mean by that? Obviously, if I want to cover this audience, I need to only think about this seat. So it would be weird for me to take the speaker and put it here. Why? There's no one here, correct? So this is just a walkway. So I'd rather cover the audience areas effectively. All right, go on. Now, in situations where sound must be reproduced outside the main system's optimum range, you need to use delay systems, correct? How many of you have used delay systems? If you delay your sound, how do you do that?
Delay system, when you have a very big hall which there's no sound behind,
yes,
and there's a PA, you delay the PA there to wait to match with the one coming from the front, so both of them can hit at the back at the same time.
So how do you do that? How do you delay?
On my own mixer, I go to the auxiliary I used for the delay system.
Yeah.
Time align it to the one. Basically, I use a system that instrument I'm very conversant with.
Yeah.
Maybe it's 9. So when I hear the 9 top, I know how it sounds. So the moment I'm delaying, I stand at the edge of the PA to listen to the boats arriving at the same time.
Okay. So you do it by ear, basically.
Say?
You do it by ear.
Yeah, and I also have a calculating device on my phone. If I know the distance I'm standing and the one behind, I put it on my phone. It gave me a timer line that I need to do.
That you enter into your mixer.
Yeah.
And then you just
apply it.
Okay. Anyone has any other approach for delaying your system? Yeah? Yes.
Thank you. What I do is measure the distance between my FOH stack and the MOH unit. I start with that. It gives me the distance. On the unit I use, it allows me to enter the distance, or if I want, whatever time setting I want. So I start with the distance.
Okay.
Then I listen to the accuracy, because I think temperature and other distance affects how the processor.
Okay.
So
okay. To what degree does temperature affect the speed of sound?
Well, I'm not sure, but from experience, I know it changes. For example, I've had to set up open air venues where I use a delay system.
Yes.
And it's not the same with the same system indoors.
Indoors.
Where it's cooler.
Okay. Okay. So that's a good thing, and we're going to address that in a second. Okay. So how does temperature affect the speed of sound? No freaking way.
When the weather is hot, it makes the atmosphere a lot thicker or denser, so sound travels a lot slower.
Oh, sound travels slower when the atmosphere is dense.
Sorry, I went faster. Faster, sorry.
Okay, thank you very much. I mean, that's a very fair, it means that sound travels faster in water than in air, correct? Sound travels faster in water than in air. You have to believe it. Say amen. Are you guys kidding me? Come on. Sound travels faster in water than in air. What you just said now is critical to that. The denser a material is, it means that the molecules are more closely packed. The transmission of energy molecule to molecule to molecule is what? Easier and closer, and it happens faster. That is why air is one of the worst medium of delivering sound. Really, it actually is. Our hearing system, if we were living if we were aquatic animals, for example, you'll be hearing things that you don't want to hear. Do you understand? Because the rate at which you're going to be faster, maybe 4 times faster than you. If I speak to you now, the time it takes for sound to get to you, if you are an aquatic animal, it will be 4 times faster. You understand? So sound travels really fast in other medium, which is why if you want to isolate an environment, what do? Create a vacuum. Correct? How many of you did that experiment in secondary school where they put an alarm clock in a jar and then they suck out all the air while it's ringing? As they're sucking the air out, it gets lower and lower in volume until you can't even hear it, even though it is still ringing. So that is, but then again, what we're talking about is the effect of temperature on sound. And like you said, he has experienced something like that. You need to be able to tackle that kind of situation. Okay, now let me give you a clue. For every 1 degree rise in temperature, the speed of sound changes by 0.6 milliseconds, meters per second. For every 1 degree change in temperature. So which means that the 344 meters per second that you use as the speed of sound, which is like a constant, correct? It's actually the speed of sound at a certain temperature. And that temperature is what? 21 degrees. Now, if you're running sound on a hot day or on a cooler day, it's going to be very, very tricky. I'm saying that because I've experienced it, basically sometime back in Europe. So you're running sound in a church, and your sound would just not want to move. You'd just be sluggish. You hear a lot of high frequencies that are just very damp, very dull. You need to compensate for that with your EQs and stuff. So that happens. And I'll show you the formulas here. Okay. Can I have the PowerPoint? Yes. I think we should back up a little bit. Okay, yes, go forward. Yeah. All right, so since electricity travels much faster than sound, listeners in the rear of the room will hear the sound coming from the nearest speaker before they hear this. Obviously, that is one of the reasons why we want to delay, correct? Yeah? Now, there's another catch to this whole thing about delaying speakers. Now, if you are delaying your loudspeaker, let's say I put the loudspeaker where Mr. Roland is standing, for example. That's where the speaker is. Now, you've delayed in relation to the front of house, correct? And use the normal formulas, work it out, perfect. And then again, you say, oh, maybe it is 18 degrees. You use the formula to calculate the speed of sound at 18 degrees. Bang on, you have it. Now, the other gentleman there that is close to Mr. Roland will still be hearing the sound coming from Mr. Roland because he's closer to it. But he will still be hearing that sound first. Because he's hearing it first, his attention is not really on the stage. You get? His attention is more, although he's forcing his brain to say, no, I have to look at the stage. Then again, the sound is getting from there all the time. So you're constantly trying to, focus on stage. No, I have to focus on stage. So that is, just keeps going on. You understand? So there's no comb filtering issues. Everything is time aligned correctly. There is no, but then again, you need, how many of you have come across Haas? The Haas, or the law of precedence effect. Okay, now Haas is what helps to solve that problem. The reason for us is this. Our ears begin to tell two signals apart from 50 milliseconds as they arrive above 50 milliseconds, basically. So if you say something, or maybe this sound lives here, and the other one, the delay gets to him, within 50 milliseconds, he won't be able to tell where the sound is coming from. You understand? So what we do is to delay the delay by the hash window. And what the hash window now does is to render that loudspeaker that is close to him transparent. So basically, you no longer hear that speaker anymore. All the sound you hear appears to be coming from the front. Even if that speaker is 15 dB louder than this one. You need to try it out. It's like magic. It is ridiculously incredible how the brain interprets sound. So you now need to look at the hash window and say, okay, I have calculated my delay. I need to apply a delay of maybe 30 milliseconds, for example, or maybe 100 milliseconds. On top of that 100 milliseconds, now add 35 milliseconds. Now that's to trick the brain to thinking that, remember, I'm trying to make this thing very clear. Remember, you've delayed the sound, correct? I mean that this and that arrive the listener at the same time. Law of first precedence now tells you that the first sound to arrive at the listener gets the focus and attention of the listener. So it means that I want the sound here to now arrive at the listener first before the delayed sound. But I don't want to delay in such a way that he would think there are two sounds. Within the 35 to 50 milliseconds window, he will think the sound, this one now gets to him first before the delayed sound gets to him. But it is not too far apart for his brain to think it is two sounds. Do you understand? So you actually think it is one sound, but this time around, that sound there, because you don't even think there is a speaker next right there. You understand? So everything, so basically you achieve your goal of focusing the attention of the audience to the stage and not anywhere else than just doing the straight delay calculations and distance and all that. Okay? The PowerPoint. Yes.
After adding your 100 milliseconds to delay the system,
Yes.
and you want to still get this one to arrive
Faster. Yes.
how do you do that? What are you going to delay to the first one? Wow.
That's what I said. Delay your delay. Delay the delay. Do you understand? So basically, you've already determined the actual delay value to allow the sound to arrive at the same time. But law of first precedence now says that the first sound to arrive at the listener determines where he thinks the sound is coming from. You understand? Let me ask you a question. If you are walking, maybe you're walking down the road and somebody says, "Hey, James," from this side, how do you know that that sound is not coming, is coming from this way and not from that way? How do you know? Exactly. The sound got here first. That's what we're trying to do. Okay? All right, let's go back. Yeah, forward. So the human ear begins to perceive two sound sources apart when the sound sources are separated by more than 50 milliseconds apart. So using the formula, distance is speed of sound times time. You can work out if we say 50 milliseconds apart, that is when you begin to perceive. If we put that number in this formula, you get 17.2 meters. What does that tell you? How do you even know you need to use delay speakers or not? Do you understand? I know for sure that I don't need delay speakers here. Because I know that before my ear begins to need it, the sound must have traveled at least 17.2 meters. So when you have a hall of maybe 30 meters, then you need the delay speakers. If you have a hall 20 meters, you may not necessarily need delay speakers. But then again, I'm just giving you a formula to guide you on when you begin to consider, that you need delays. Okay. So in our PA example, no need to do this calculation. Okay, for TF, obviously, like other digital mixing consoles, it's not unique. Enter distances, it will give you the actual delay time. You understand? But I don't do that. I rather use delay time, in which I have already calculated my hash window into it. Okay? But, okay, sorry. Back up a bit. So you can see here, to determine the speed of sound at any given temperature, we apply the formula C is equal to 331 plus 0.6 times T. So this is the way you determine the speed of sound at any given temperature. T will be the measured temperature that you're going to insert into the formula. Okay. The Haas law, if two or more versions of sound are produced, the first one to arrive at the listener's position will, in most circumstances, determine localization. So you need to research that, and you'll see. This will remain accurate for delay time shorter than 50 milliseconds. Two or more display signals will be perceived as one sound originating from the direction of the first signal to arrive. This is valid even after the latter sound is approximately 15 dB louder. That is significantly louder than the first. Okay. So check this out. How much delay needs to be applied to the reinforcement speaker to ensure correct localization? Use hash delay of 20 milliseconds. Can you do that? Can you even see that? Okay, anyways, we can send this to you by email, so you can, yeah. So let's proceed. For subwoofers, when two subwoofers are arranged on each side of the stage, there can be a buildup of energy resulting in power alley. Okay, now let's do something, yeah? Something practical. Something practical. Can you send sine wave to the subwoofers? Hold on. So I'm going to try and send sine wave. No, wait. So sine wave to the sub here. Okay, cut this out. Check, check. Okay. Now, I heard, I think, that there's some subsonic frequencies, that can be used to make you feel uncomfortable. You may not be able to hear it, but it's just there. And just can, psychologically can be very, very nauseating. You understand? Sine wave can be like that. But generally, the point I'm trying to make is that, so when you're looking at subwoofer configurations, left and right may not be the best. But then again, why would you even do left and right subwoofer configuration? Why? Because the pastor has instructed you that, look, that's the way the subwoofer must be. You have no choice. You understand? I'm just, or in certain situations, the way the hall is built up does not even allow you to, So, but usually, if we took these subwoofers, the DXS 18s, we'll put them in front here, for example, side by side, and then reverse turn maybe one of them to face the stage, invert the polarity, and delay that speaker by the depth of the loudspeaker. That's what they call what? A cardioid loudspeaker configuration. And what's the purpose of that? To give you a much more forward thrust and cancellation on the stage. So these loudspeakers have cardioid configurations inbuilt. So you don't necessarily need to do all the hard work. So just put them together, press cardioid, and go to sleep, basically. So we've done all that work for you. PowerPoint, please. Yeah, so that's an example of the radiation pattern of a cardioid subwoofer, and the DXS 18 has that inbuilt. All right, let's go. Now for subwoofer alignment, obviously, this is a way you can, if you have the subwoofer a bit, spaced from your main loudspeaker. So basically, you take a measurement, you go to the sweet spot in your hall or in your church or wherever, and measure the distance to the mains and to the sub, and deduct basically the same principle and process used to apply delays. You can delay the subs so that it actually matches with the mains. Let's go forward. For this kind of setup, for example, do I need any delay on the? Do I need to delay subs or anything? No. So it's kind of in phase. Yep. For tripod mounted, so this is kind of standard, based on approximate measurements of the tripod, so you can use 3.3 milliseconds. You can align your subs to your mains. Same thing if you were on stage. Those are just rule of thumb, but still measure them to get your results. You know how to do that already. All right, let's go. So rigging, like I said before, a lot of the time when we design systems for churches, or we forget this part, forget wiring, what is the speaker gauge, we forget some of those things, and you want to always keep that in mind, the required rigging for your PA system design. All right? Any questions so far? Yes.
Thank you.
Yes.
Sir, I want to be clear about the cardioid position of the speakers you just mentioned now.
The cardioid?
Yes.
Okay.
Because in my own setup, for instance,
yeah,
just like what you have said, most of the time it is the pastors that dictate where you mount the speakers. Okay. As a matter of fact, there are too many hard surfaces in my church, and we are trying to work on the acoustic.
Okay.
And the pastor has said the general overseer was the one that came to anoint that altar the day they were doing the dedication, and nothing can make them put rug on it.
Okay.
Now, this is so we have a situation whereby the subs has to be lapping on themselves, and sometimes, in fact, most times, I get angry with the dryness of the output I get.
Okay.
But there are two questions I want to ask now. Number one, I want you to help me to expand on the cardioid positioning of the sub. Then secondly, is it ideal to mount the whole of the sub in a corner of the church? For instance now, if we are building a plank stage here and we want to make the sub invisible, and we decide to plant it under
the stage.
Now, will the output of the sub on the overall output of the house not being one-sided? Being the fact that the sub is on one side of the church.
Yes. Okay. Actually, it will if you follow inverse square law. Yeah. So if it's on the corner, obviously it's going to be louder down at that area. Now, but the good thing with subwoofers, obviously, is because of the long wavelength of subwoofer, so they can diffuse, they can, so yes, they can really get around very easily. So, yeah, you just every Sunday when ushers people to sit in that side of the church, it will they will not be very happy. But the other guys that are somewhere around there will love everything that's going on. So during church general meeting, while these guys are complaining, these guys are celebrating. Yeah. So how do I put this? The pastor has gotten revelation from on high. We can't argue with that. So just comply. Thus saith the Lord. In spite of all your physics and your sound experience and all that kind of stuff. I know, I mean, I've experienced stuff like that before too, and what can you do? But subwoofers, yeah, you can get away with it just by the virtue of the wavelength of the sound. But that corner will always be hot. All right. Okay, go on. Yes.
For the benefit of some of us who don't understand a lot about delay, one question here was, when you loop your speakers, can you still delay? That's the first question. Then another question is, do you need special speakers
for delays
when you are doing delay?
Okay, number one, do you need special speakers? It's always good to have special speakers. And an example of special speakers is our Yamaha. So that answers that question. Yes. The first one. Yes, of course. I'm not going to. Oh, geez, I'm coming to. I have to talk about my speaker first, obviously. Forgive me for rearranging your question. All right. Now,
when you loop,
that was the first one.
That was the first
that I have demoted.
Yes.
The second one.
That was the first one. So
I'm going to answer that now.
When you loop your speakers, can you still delay?
Okay. Now it depends on. You are delaying to make sure everything is in phase, correct? Now, but if you're looping on a line, yes, so you have to. The same delay applies to that same line in relation to the mains that you are. Let's say you have 3 subwoofers here now. You have looped, and you have your main tops. So those 3 looped naturally will just be in phase with that one, correct? Okay, let's say you have 3 here, and then you have another 3 somewhere around there, and they're all looped. It would be a very bad idea to loop with those ones because they will be out of phase with yes. So it depends on what you're trying to do. Okay.
Yes, my question is, with regards to delay. I have a
Seriously,
wonderful-
guys, you guys are delaying this seminar.
Okay. I have a unique system,
Okay.
line array system, 5 arcs
Yeah.
of 3, 2, oh, sorry, 3, 3, 2, 3, 3. That's 4 sub and 5 tops. In what way will you apply delay on those stacks? They're all like facing front of house.
Yes. Okay, now I'll use this line arrays, the one we have here, to explain that. You know, there are 3 M28 stops there. In the middle, you have the B112, which is the base module, and then at the bottom, you have the subwoofer. Then let's say you have to delay this in relation to some other, Now that has to do with how you wire those modules to your amplifier. You understand? So let's say, in our case, for example, those 3 tops go into one channel of the amplifier, and the base goes to another channel, and like that, So, and each of those channels, the 4-channel amplifier can be delayed individually. So it depends on how you make your stack and the wiring to the amplifier, and if it's a digital amplifier, and all the presets you can get from them, or you can enter your own delay values. So that is accounted for in the speaker or the amplifier software as well, if it does have one. Okay.
Okay. Good morning.
Okay. Okay.
Okay.
I greet you. Okay, let's go.
Okay. Let's say you already have your audio design for like 500 people, just like you mentioned.
Why are you? Believe God for a bigger church. Okay.
Okay. Then 2,600 watts less amplifier with your speakers to match.
Yes.
Then an occasion now arise that you need to feed some other people, maybe outside that place.
Yes.
You now need to loop. So what would be the implication of looping on that particular system?
This is simple. You blow something. There will be a blowing of something, whether it's in the loudspeaker or. I think I've just answered the question now. Okay, let's move on. No. Just to take it seriously, to take him very seriously, Once you've designed your system, obviously you know the limits. We've already given you, okay, this is what your impedance should be. This is what your power should be. If you're going to be adding another loudspeaker to an amplifier that's designed to take 4 ohms, you're going to be changing that impedance balance, correct? And you're going to be causing trouble, isn't it? So, which is why, if the man of God tells you Jesus Christ fed 5,000 with 2 fishes, you have to produce sound for everybody with this, just tell him you are, tell him you know that greater works you are supposed to do. But in this case, I humbly decline. Yes, but a different day, different time, you will do greater works. But this one, thank you, sir. Okay? Or you have to give him more tools to expand the system. Or make sure when you're designing in the first place, the system is scalable. You can scale it up, scale it down, without too much overhead costs, you know. And that is why the STM system there is an amazing system. It's scalable for. But you get what I'm trying to say. Yeah. All right. Okay. I think I will. Okay. Can I have my PowerPoint back? Because I have a couple more slides before I'm done. Okay. This is where I stop. How many of you have calibrated the systems that you're using or that you currently use? How many of you calibrated it? Hello? You are the only one. You are the only you. Jesus. Praise Lord. Who else? I'm not seeing any other hands. Oh, yes, okay. In fact, I count two of you as one. Oh, you are there too. Okay, good. Yes. No, that's one. All of you like that. I only see one person. Okay, okay. Oh, you calibrated yours. Awesome. I'm so sorry. So what was your process? He needs a mic. Oh. Yeah, please go on. A mic will get you soon. Yeah. You want to? Yeah. 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 Yeah.
So basically, if I want to be lazy at that time, I just want to run the setup quickly. Maybe there's no time to. If it's a small gig, I'd usually just go with the Venue 360 processor.
With the
Plug
what?
my Venue 360 DBX.
Okay. Yeah.
Plug my RTA mic into the RTA port of the processor.
Yes.
And just let it calibrate itself and make necessary adjustments as I see fit.
Okay.
Or want to be more precise and it's a bigger gig,
Yeah.
just I'm sure that as they would have done our experience. Just we go with something more professional like a SIM.
Yeah.
Check for first of all, your system has to be as flat as possible. You have to have a flat frequency response as much as possible. Make sure that there's no cone filters and make sure that your system is aligned as the different
Yes.
graphs will show at that time.
Yeah.
So that's what I usually do
To calibrate
calibrate the system. Yes.
Okay. Now, what are the parameters that you have in mind when you're calibrating the speaker?
Well, usually, to be honest, what I usually just do is just
We only want honesty.
flat frequency response.
I'm not messing with you.
Flat frequency
Go
response.
on.
Flat frequency.
Flat frequency response. Okay, you seem to be talking about optimization.
Okay.
I'm talking about calibration.
Okay.
Yes. I get what you're saying, flat frequency response, cone filtering, delay, and those are how you optimize the system and make sure that it is delivering, the best possible sound it can deliver.
Yeah.
But then again, it's going to be delivering sound at a certain SPL level, and you want your loudspeaker not to be blown.
Yeah.
So calibration is more or less trying to say that this is the limit. My mixer is not going to produce anything at 0 dB unity gain. My mixer, if I push it to that point, it will not be my loudspeaker should not be at risk in any way. That's calibration.
Okay.
So how do you calibrate your speaker to make sure your speakers are safe, your tweeters are safe, and they don't get fried?
I'll leave that to you to answer.
Okay. But what you just said now is rich. Thank you. Yeah. Anyone else? Okay. many of you have had the courtesy of blowing some tweeters in your church?
I want to believe that every one of us that are here today, we are here to learn, and it will be the best for the benefits of us as an individual to say it the way we know it is.
Yeah.
So that the professionals that has put this together will know where the shoe is pinching everybody. So I don't believe in know it all.
Yeah.
And I don't believe in keeping quiet when it comes to something that has to affect my destiny and future.
Amen.
My own answer to that question is that for the speaker to be safe from being fried up, in my own literal understanding, based on experience, I believe that number one, the speaker and amplifier matching is very important to be considered.
Sorry, just to calibrating means you've done due diligence. You match power, you match impedance, it's flat, it's delayed, all that is fine.
Okay.
You're perfect.
Okay, now it has to now do with how we do our the sound check, the gain control. Because if, for instance, if the gain control is clipping from the start, what used to be the suffering end first is the tweeter, the high frequency.
Okay, let me just chip in. You're talking about limiters.
Yeah.
Not gates.
Yeah.
Okay, go on. Yeah.
So now, when this is done, and the overall volume control and the gain structure of that particular sound system is not clipping in any way, there is no how, and you have your limit on your master fader. That is the maximum the volume can go, even though there's an headroom. So in case if the show is hot, maybe there are headroom of 3 or 5 dB, and you get to that 5 dB, you still have a clear signal, clean sound. There is nothing that can fry the speaker.
No shaking.
That process.
No shaking. Everything will be. Okay, I get what you're saying here, but I promise you that, with all that into consideration, people still destroy their loudspeakers. Calibration.
Well, I've not done it before, but I've seen the using an XPL meter.
Good.
To calibrate. I've not done it, but I've seen someone
do it.
Yep.
That's fantastic. That's where we're going to. That is where we're going to. Because when you want to calibrate, you have to. There's something that must be at the back of your mind when you are doing your calibration. What was the purpose I put the system together in the first place? Speech and music, correct? Now, in every system design, there are guidelines and the guidelines you use for your design process. You're going to say, okay, something like, I want minimum variance of 3 dB across the entire listening space. What does that mean? No matter where you're sitting in that auditorium, what you're hearing in front is the same thing you're hearing at the back, correct? So you can say, okay, I want a 6 dB minimum variance. Then you design your system accordingly. Which means that you're not going to be putting as much firepower in the system like you would do if you're looking for a 3 dB variance, correct? Sometimes you do 2 options. You do one option, 3 dB. If they have resources, they can do that. If it's 6 dB, they can, so give them options. Okay, this is higher end, this is, So, that is one thing. So, when you're putting your loudspeakers, you're trying to achieve that. When you look at the dispersion of the sound when you run your simulation. Okay. So that is a guideline, because I can't just be designing without purpose. Now I will say, okay, I'm designing this system for Chevron Nigeria Limited. Definitely I'm not going to be putting the subwoofer there, correct? It is for what? For their corporate meeting, speech, right? And I don't want to give them 100 dB SPL of sound when they're just trying to have a conversation. You know? So I would say, okay, what is good listening level? You know, it's okay, good, 70 dB. I want to up that a little bit by 10 dB just to give them some. So I designed that system by that much. Okay? Now, for big PA systems, you know, you want to say, okay, usually for rock and roll, you're looking at about 100 dB SPL. We have heavily compressed music, heavy subwoofers, you know. And in that case, you're not going to be doing 1.5 to 1 subwoofer ratio anymore. You disregard that and do 1 to 1. One subwoofer for every box because it needs that punch, correct? Now, for church situation, a lot of the times it's usually around maybe 90, 95 dB. If you're doing 100 in church, one day pastor will just call for prayer meeting and just say, okay, let us pray for our engineer, you know. But then again, so I know that, okay, I want to calibrate, my system should be optimum at maybe 95 dB. Yeah? And I don't want it at any point, at any given point, to exceed that. Yeah? Then you calibrate your system at 95 dB. So that even if you have a visitor engineer, you have volunteers or whoever uses the system, that person will not be able to exceed that calibrated level. You understand? So that way, it's an extra protection for your system anyways. Correct? I know we do, you know, you have to put your limiters, you do all the processing you need. Yeah, that's fine. But then again, you need to calibrate your system. And it's very simple, like it says. You use an SPL, this is how to do it. And I'll just try and run through, you know, from my mind. Your loudspeakers, like this one, for example, we turn everything down to 0. We turn everything down. Yeah? After we turn it down, we come to the mixer and run pink noise at 0 dB from the mixer. Yeah? And then run our master fader at 0 dB. Okay? We just, at this point you are hearing nothing, correct? Yeah. So you now go with your SPL to like the sweet spot in the middle somewhere there where the camera lady is standing, something like that. You know, and then you take your SPL level while somebody is raising the speaker. Once it gets to 92 dB, stop there. Stop that, feel that. Do the same for this guy. Once it gets to 92 dB, stop there. Why are you stopping at 92 dB? Why? Sorry? Headroom? Headroom. No. It's because, I told you before, when these two are on together, in the middle, there's a 3 dB bump. Yes. So it will certainly be 95 dB when the two are working together, correct? So that way, remember, your fader was where at 0 dB. Which means that once everything, you normalize your system and you mark all this, if you push your fader to 0 dB, you are only at the calibrated level. So there is no way on earth your system can fry. There's no way on earth your system can give up on you at any point in time because you've properly calibrated. So you do the same thing for the subwoofers. You understand? So that way, you know, you can safeguard your system and make sure it is. Okay, I'll take one question before my time is up. Actually, wait. Let me get him first. Yes. No. Active speaker has the amplifier inbuilt into the, yes, and there's a volume at the back. It doesn't have volume. Okay. You don't have software. Exactly. That's where you have to work from. If you have a passive speaker, you go to the amplifier. Like this STM system, for example, if it's flown, there is a software called Nemo that manages the amplifier, so I can do all that from there. Yeah. Last but not the least.
Because of the lecture, you mentioned that there are some space that is very difficult to determine the left and the right.
Mm-hmm.
That, like, in such cases,
yeah,
how do we determine the calibration of the speakers? Because, like, the speakers are scattered everywhere. I've been invited to set up in such a place before. You don't even know where to hang speaker. They just mount them all around the whole place, and and there was only one line array in the middle of the church that they hang. So, and this is not a theater setup. So the line array is now connected to a speaker management that represents the FOH of the church. So practically you don't even have a sweet spot.
Okay, good. It's still, okay, good question actually. You seem to be getting all the juicy projects, which is great. But let me tell you something here. When we talk about left and right, we talk about sweet spots. But there are other speaker configurations called distributed systems, correct? There's no sweet spot in that kind of situation. Your sweet spot is proximity. The speaker that is feeding the area that is intended to cover. So that is the sweet spot. So in which case, if I'm calibrating at 95 dB, I go straight to 95 dB. You understand? I'm not going to 92 because I'm waiting for the other to come in. So you calibrate as per the speaker for distributed systems. Yeah? Okay, so I think we have to call it a day at this point. So thank you very much. Thank you.
Thank you very much, Mr. John. I'm sure if we stay here for another 5 hours, we still have lots to talk about. Please a round of applause for Mr. John Oben. Like I said, we still have a lot of topics to cover. We still have a lot of information to give. But at this point, we want to just take a break for the morning session so we can at least refresh ourselves. And then we can come back for the afternoon session where we have more practical demonstrations on especially our digital mixers. So we'll have more understanding in terms of what he has been saying all morning. So I would crave our indulgence if we just walk towards the exit to my left. We have table sets already. So we'll just have some light refreshments and come back. We're taking around 45 minutes for this break. So we're back here at 15 minutes before 2 p.m. So thank you very much for your time. So I'll see you in 45.